Hello students, welcome to class 12 physics. In this video, we are going to discuss the Faraday's law of chapter number 6, electromagnetic induction. In the last video, we had seen the Faraday's experiment, right? And in that experiment, we had seen that when you take a bar magnet near to the coil, right, then what happens? Because of the varying magnetic field, the current is induced in the coil, right? So in the same way, when we take the bar magnet near or away from the coil, the current is induced in that. Now let us see the Faraday's law. The statement of that is the magnitude of the induced EMF in a circuit is equal to the time rate of change of the magnetic flux through the circuit. See, we had seen that if the magnet is taken very fast near to the coil, then more current is induced in that. And if we take the bar magnet with less speed, right, that means current induced in that is less. So it depends how fast you are taking the bar magnet near or away from the coil, right? So here also what happens, the rate of change of the magnetic flux through the circuit is nothing but the EMF induced in the coil. Now first of all, let us see what is magnetic flux. Magnetic flux is nothing but the field lines, the magnetic field lines in the surface area, right? That is called as the magnetic flux. The field lines that is linked with the surface, that field lines linked with the unit surface area, that is called as the magnetic flux. Now what happens when you are applying the magnetic flux, right? When the magnetic flux is changing with respect to time, magnetic flux is changing with respect to time, that means when you are taking the bar magnet near to the coil, right? Let us consider a coil, right, with one turn, right, that is a loop. When we take the bar magnet near to that, then in the particular surface area of the coil, right, let us consider this as the area element, right, then the magnetic field lines, right, linked with the elements will also be changing. As you take this bar magnet near to the coil, then what happens, the magnetic flux will be increased. So the change of the magnetic flux with respect to time, that is the time rate of change of the magnetic flux, it will do what? It will induce EMF in the coil, and due to which the charge comes in motion, which is called as the induced current. So here the magnitude of the induced EMF in the circuit is nothing but the time rate of change of the magnetic flux through the circuit. And mathematically it can be written as epsilon equals to minus d phi b upon dt. So here d phi b upon dt, that is time rate of change of the magnetic flux, and here epsilon is denoted for the induced EMF. Here the negative sign indicates that the direction of this induced EMF and the direction of the current in the closed loop. In the case of a closely wound coil of n turns, change of flux associated with each turn is the same. That means if you are having n number of turns, instead of one turn, if you are having n number of turns, then the magnetic flux linked with each turn will be same. So for that you can write it as epsilon equals to minus n d phi b upon dt, that is EMF will be number of turns into minus d phi b upon dt. The induced EMF can be increased by increasing the number of turns n of a closed circuit. So you can see in this equation that the EMF is directly proportional to n. So if you increase the value of n, EMF will be increased. So increasing the number of turns of the coil will increase the induced EMF. So students, you may note down this theory.